All right, this is the second video for electrophilic aromatic substitution. Intended just as a quick practical guide for what we've already really covered pretty much in depth. I've got the chart over here on the right, and so let's just say we start with a derivatized benzene, so in this case carboxylic acid here. Of course, the implication is that you know that CO2H is the same as C double bond O, OH, that's a given. And we look over at the chart, and that clearly shows to be a moderately deactivating meta director. So it's going to direct the chlorine in this addition meta, and if we add 1 molar equivalent of these reagents, you should get chlorine adding there. If you added a second molar equivalent, hypothetically, then you would expect the chlorine, an ortho-para director, to probably take over, since those are basically less deactivating. And on the chart you can see the chlorine is weakly deactivating, whereas the carboxylic acid is moderately deactivating. So in the battle between carboxylic acid and chlorine wins. And I would expect the second chlorine to either go here or here. I'm going to vote for this position being the least sterically hindered, although the other positions are really not that sterically hindered. So I think, you're probably going to get a mixture here. But in a case like this, I think I would expect the second chlorine maybe to go here. Well, that would be a reasonable answer. And you can keep going with more molar equivalents, but it gets pretty complicated. And you run out of positions then, actually. So, looking at the next problem, we start with benzene, and we're adding first a bromine. So that's just brominating the benzene in any position. And I'm assuming 1 molar equivalent, unless otherwise stated, for each. So we can envision a bromine sticking on here. The bromine is a weakly deactivating ortho-para director. So the sulfate group is going to then add probably para. So this is an easy one. You'll have the bromine and then a para sulfate, most likely. Maybe some ortho position sulfates being produced, but I think para is probably better. Both would be acceptable answers, though, according to the chart. Notice that if we had added the sulfate first, that's adding a meta director, according to the chart over here. So, the meta director sulfate group. And so then we would end up with the bromine meta to the sulfate rather than para or ortho. So thus the order of events being chosen. Really only wanted to show one more example because I think you already got the type of thinking involved. This is along the lines of, hey, we want to make this starting from benzene. Only you've got some clues here. So you can envision that this bond has to be created at some point. Clearly, there's a reduction step which suggests Friedel-Crafts acylation. Because that's in that method. You have a carbonyl group that then gets reduced in the second step. So it's pretty much clearly pointing out that we're doing a Friedel-Crafts acylation. So what's being reduced then is this material, having added via Friedel-Crafts acylation. And so our Friedel-Crafts acylation product that goes here, reagent, excuse me, would be simply the chlorinated, the version of this. And we call this group, incidentally, an acid chloride. And if it was a bromine, it would be called an acid bromide, and so on. So that's what goes there. That's the missing reagent. Remember, that forms a complex with the AlCl3 minus plus which then forms an acylium ion there's our AlCl4 minus floating around, and the acylium ion, which is basically, should really be drawn linear, plus charge on the carbon. That makes it a strong electrophile for pulling electrons out of the benzene ring. So drawing some long arrows here, we can draw electrons out of that benzene ring to the carbonyl of the acylium ion directly. One arrow gets us to this material right here. So that's really about it. You want to be able to, given something you want to make, like the product here, be able to visualize the bond that gets disconnected in retrosynthesis. Envision your carbonyl group here. Here's your imaginary carbonyl group from whence it came, right? And then imagine, and the reduction is really the clue here. So how would we know that we need Friedel-Crafts acylation if we didn't have that clue? Let's just go ahead and do that. You know, the answer to a lot of these questions is like, well, let's see what happens when we do that. So here's our benzene. We want to add that group. So we're going to say to ourselves that we're just going to do Friedel-Crafts alkylation, excuse me. AlCl3. Just checking the group. 1, 2, 3, 4, 5 carbons. Yes, 1, 2, 3, 4, 5 carbons. We expect this then to form AlCl3 to form that reagent complex AlCl3 minus plus, and then we draw in these hydrogens and realize that, oh, we can have the much feared hydrogen migration. That hydrogen goes over with its 2 electrons, kicking off this great leaving group, which ends up giving us, okay, wait a minute here. Okay, sorry about that. Giving us a tertiary carbocation, stable tertiary carbocation. The AlCl4 has left. 1, 2, 3, 4, 5 carbons. So that creates a methyl on the end, if you notice the hydrogen when it migrates. And then, lo and behold, the benzene can react with this strong electrophile, resulting in after the elimination step, of course, an unwanted, undesired product. So if you're given this problem where you're asked from benzene, how do I make this product? You could go ahead and try the Friedel-Crafts alkylation like we just did, and notice along the line that this phenomenon down below can happen. And so you say to yourself, well, I'll avoid all that by doing Friedel-Crafts acylation. And that's about it. So just sort of a regular length video, few loose ends to tie up on some practical considerations.